These are the traffic lights that do somehow self-control. And putting it in the motto of the workshop, the past to the future. So how to turn an idea that we had in the past into a successful future. And also this controversy is like, it's great to have this chance of doing this, but also having the burden of this responsibility to be the one who carries it through everything that is necessary to bring it into practice. And this two-parted story is also the structure of my talk. First is the inspiration and the methodology, and I hopefully convince you how successful all that is. But the second part is what really struggled me and still does, and what is the challenge and also the limitations. When I came to Turk's team, the big words were self-organization in nature, in pedestrian corridors, and so forth. And you observe, for example, in swarms, the rotary motion, and that's what we have in cities. It's in the traffic, the traffic circles, roundabouts. Or when pedestrian streams cross, they do not stop and wait for each other. They have a region where they go in the seemingly same direction, but they turn from left to right and leave the crowd into opposite directions. So they intersect without stopping. Well, this you can have in cities. It's in Barcelona, for example. Crossing streams go into the same road, a one-lane road, one-way road, and they switch lanes and have intersected in this way. And on corridors with a small door and pedestrians coming from opposite directions, only one side can pass, so there's some oscillatory movement, and that's what we have in the city as well as traffic lights. The last thing, the corridor with the pedestrians and oscillating, they behave as if there were a traffic light, but a different kind of traffic light, not a traffic light that we know from the street. Because that traffic light is fully actuated. If there is more pedestrians coming from the left, there's more green automatically. If there's no one coming from the right, the lefts, they are free, there are no hindrance at all. When one side releases the pressure, like there's a gap, the other side comes in. So it's highly efficient. Time is used to its maximum. And if you study it more closely, this alternating behavior also has optimality properties. And that really fascinated us, and we formalized it, tried to find some generalization to bring it then to complex traffic intersections. We did our first studies, and the results were quite promising. We patented it all around the globe. Crazy. I did my PhD on it. We put it on the field, and the results kept being great and promising. Others saw it. The Golden Swiss gave you the award for that idea, and I dared, together with Christian Heimgartner, to found a company on that. And here's a list of some results that we had. And for different modes of transport, you see the numbers that give the percentages in total waiting times that we reduced. And you see, it's not that we take it from one mode of transport to improve another. It's for pedestrians, as for cars, as for public transport, where we significantly and in high numbers reduced the delays at the intersections with that approach. Traffic experts said that is not possible because they know and they learn it, and every traffic engineer knows Webster's curve, that's not possible. When you control a city network, the traffic lights need to synchronize, so you have kind of cycle where everything repeats after 60, 90, whatever seconds. And they know the optimum because what does this curve tell? It shows the total delay over the cycle. You cannot make the cycle much shorter. There is a limit, which is due to the switching loss. You have the intergreen time, and in the average demand, you cannot switch faster than a certain value. Why does this curve go up on the right-hand side? Because if the cycle is too long, the red times get longer as well. But there is an area in between. And that is what you need to cope with randomness when you have a cyclic control. If you expect 20 cars per minute, you don't have to, could be that there's only 18 cars coming or maybe 24. So you need to let some luft for the system, not that the queues get too long, because that's why the curve goes up and on the left-hand part. But randomness is only that there's something which you do not know. But with detection plus a good actuation, why should not go for that point? And that is where we get the savings from. Put it in a different way, there are two queues and they are alternatingly queued, and then you have this trajectory. One queue is cleared. An ordinary traffic light has to stay green for a bit longer on average before it switches back. But that point here, that's a global attractor. If you have detection that says, okay, the queue is cleared, now switch immediately. And that is a global attractor. No matter where you start, how you disturb the system, it goes back to that blue point. It's a very simple model, and we do some optimization on it. I will briefly go through the model. There's a street, cars coming from top to down. We bring the time axis. You see the trajectories, traffic light switches to green sometime. And the traffic passed an inflow detector, so you can derive some curves, an arrival curve, departure curve. The difference is the number of vehicles being delayed. The area is the total delay that we are going to optimize. That's the model. What does the controller do? A model-based controller at some time knows what the detector said, knows the arrival curve, assumes when it's green, the cars will flow out at maximum rate. It can predict when there is free traffic. And it can derive how much cars do I have to serve in order to clear the queue, how many stops will occur, and what happens if I do not switch now, but 1 second later, because that n hat, the number of cars I need to serve to clear the queue, that's the amount of cars that will be also delayed by 1 second if I delay red by 1 second. And because that principle is so simple, I dare to explain it with, or to show it alternatively with tic-tac. Others try to explain inflation with tic-tac, but it's Swiss tic-tac, that's Ricola. So here's the red light, one car is standing, another one, and here's a platoon. Traffic light is red. If I wait 1 second before switching to green, one car has to wait. If I wait another, I squeeze out the gaps. After 3 seconds, the 4th second is worth 2 delay seconds of cars, and so forth. I squeeze out the gaps. And here, click, click, 2 more stops. From now on, after so many red seconds, the next seconds will imply 4 delay seconds. So you can derive integrals, and that makes it, that's the key, so numerically efficient to evaluate a huge solution space in an instant to apply rolling horizon. So every second the controller does what seems optimal over the next 2 minutes. By going through the huge solution space without restrictions like cycles and so forth, or traffic phases and fixed order and so forth. So we call it self-control because the traffic lights know themselves what is best to do. You do not need much of configuration, and that's what you need is only describing the system. There's a detector, there's a traffic light, and the basic boundary conditions. But you do not have to define the behavior, like the left turner needs 10 seconds or whatsoever. No, the dynamic behavior derives automatically by the demand. And sophisticated patterns arrive surprisingly. For example, if a bus comes, it moves away the queue of cars in front of it. The bus has just a weight 20 times higher than a car, for example, and the weight you can choose freely. Or if serving a bus takes a long time, whatever, or 2 or 3 buses, the traffic light switches some other streams that are not conflicting in the meantime. Or you have a pedestrian crossing over 3 lanes with islands in between, but pedestrians should not stop in between. So normally, if you give green, all 3 lanes have to have red all the time. The pedestrians need to cross all that long path. Self-control looks at such solutions. If one lane is more congested or occupied by cars than other, so one pedestrian and then stops earlier. So depending on the demand, different solutions emerge without having them to be predefined. And this is where the benefit, the potential comes from this flexibility and freedom. We had some early doubts, or others had doubts. For example, can such a controller fulfill all requirements? And I said, yes, so far, okay. The most challenging ones were those with blind pedestrians. They have acoustic and vibration and special safety timings, but notice you can all describe this with boundary conditions, no problem. Is such switching not too chaotic? Well, it's provenly chaotic, but it's much more natural. You look at the traffic, and if conflict is cleared, you expect to get the right of way, and that's what this traffic light does. You do not expect to wait 60 seconds, but you expect to have the right of way when there are no conflicts. And does it coordinate the networks? Because it's only a local controller for a single intersection. Well, next slide. Of course, because we have some local interaction. One is the traffic itself, but also the intersections communicate. One is telling the other the amount of traffic it is about to serve in near future. And the other one is telling the available queuing space, which becomes available in near future. And it's just a modification or generalization of the arrival and departure curves. So the method underneath is the same as just presented. And well, it's an emergent pattern, this coordination, because green waves emerge whenever it is possible and if it makes sense, because stopping a large platoon is associated with a high cost for the optimization problem. Small platoons are sometimes stopped and joined to larger ones arrive. And this picture also you saw yesterday, on top there's a classical perfect green wave, and the top one is the self-control. It looks more chaotic, but in the sum, the total delay and also the stops are on a much lower level. And I said now, if there's a gap in platoons, and there is a gap in between, those opportunities are used for pedestrians to cross or for a side street to come in. Those gaps, the greens are not wasted like holding green while no car is coming within the gaps. Okay, I wish I could convince you so far that this is a great idea and a great success, because it's all not that easy. I faced some problems, some I expected, some I did not expect. I faced some challenges and problems, some of which I solved, some of which I have not solved yet. And just to give you, so I flipped the coin, so we could look at the backside of this methodology a bit. One very simple example is unexpected and not yet solved, for example, the gaps in the platoons. Car traffic is not only normal cars, could also be a truck. And a truck pollutes noise and dirt, and it takes long to accelerate. The cars behind, they are slowed down, and it leaves a huge gap. If you apply this to the network, the truck is likely to stop at every intersection and to lower the throughput. That's terrible. No, it's not so terrible as it sounds now, because the number of cars is few, but most likely a truck is being stopped by the self-control. It needs particular sensors for that, but we do not have yet. That's an issue at least. Okay, to the throughput. Optimization is worthless if traffic does not get through, of course. Our intersections are 1 or 2 days per day oversaturated, where you're at the maximum. This could be also just a temporal concentration because people have to want to be at work at 8 and leave at latest possible at home. So somehow it concentrates, not only for the volume over the hour, but you have such peaks, and if the demand reaches the capacity, even with a classical controller, the total delay goes up. But with the locally optimizing controller, it goes up much earlier. So we are really great at low traffic. Medium traffic is okay, but terrible at high traffic because there's not much space for doing errors. The higher the demand, the less error is allowed. And this local optimization does not have the freedom, and the freedom it uses often are those errors and taking away the capacity. For example, there's a bus coming and the pedestrians are waiting. Okay, the bus is rated high. The pedestrians will be served soon. Okay, there's a next bus coming, or there's a large platoon and pedestrians are postponed, and that's not really nice. But we found rules, it was also in my PhD thesis, how to overcome this. And this is what you need is a supervisor that observes those critical states and only in the right moment, and no longer it implies the right thing that overrides the optimization. It's like pulling the lash and say, okay, it's well what you just did, but it's enough now. Look here, it's important also. So we overcome this, and we are on this black curve underneath. Now let's talk about this one-dimensional optimization, where we also learned that this is maybe not enough for what we really need, and I would to put the focus on it is not even fair. What does it mean, minimizing the total delay? And remember the example I showed you here. Was there any sense of how long that car waited here already? The total minimization looks only in the future, not in the past. It has no sense of how long someone waited. And if it's only about reducing the number of delayed items in average, and they arrive and you take some out, you do not care if one is waiting forever if it helps to keep the average level down low. This kind of local minimization is even stateless, has no internal state. The state is external, the queues. If some queue would not resolve for some strange reason, the controller would not switch. So we need some supervisory rules, and those be implied, and so it becomes better. In the peak hours, also the pedestrians are on a higher frequency, and switching to pedestrians lowers the capacity for cars. Queues can spill over. You can, if they come over a critical cross sections, the queue is stuck there, cannot resolve. You can even have gridlock effect. So the inflow goes up, the outflow goes high, inflow goes higher, the outflow drops. That's the urban gridlock. This is what you have on such left turners. If the traffic volume go up, the left turner can block the main road. Or if you serve it particularly, it blocks the other one. So you end up with no one is happy but the left turner. That's the king of the road. An unnecessary left turner dominates everything. Yeah, sensors, all modes of all modes of transport have sensor detector issues. So they need attention. As boring as it is, they need attentions. I go quickly. Sometimes you have signals from buses that are not even there. You give full green, but there is no bus. Everyone waits at the intersection, nobody knows why. But the detection and the recognition of traffic states, that's actually where I believe artificial intelligence could improve that system. What also is a challenge for us as a company, our projects are in the public sensor. So you have many people that you have to talk with and convince with. There are complex decision chains. that I do not always understand, and there are different people and different decision chains in every city. Cities expect much, but the budget is limited. They expect that we have a nice web GUI, an interface for monitoring and tuning. We developed it, I used it, but no city ever paid us for this. We are a critical infrastructure. Some cities provide us remote access, others not. If there's an issue, I travel there, stand on the road, wind, weather, noise, with the laptop and analyze what is, whatever, and fix it in the hotel room and travel back on the train. All that is challenges if you really bring that idea to let it work on the street. What are the perspectives for the future? 4 items. One is, I want to use artificial intelligence to bring it on the sensor detector side. Detectors are erroneous and incomplete, and I wish artificial intelligence could help. With an but I don't think that the optimization core should be replaced. I have much trust on what runs in the core, so it's on the input. The methodology, I want to have this concept of fairness within the core, not as a supervisor, but maybe that's the best solution, but this needs to be find out. And maybe to extend the local optimization to widen it up in the direction of a global optimization. Demand management. So if there comes too much traffic, maybe some of the traffic we can, for good reason, hold back. And the freedom that we give, like less waiting times and so forth, maybe we can shift it to the modes that we want to support. So keep the quality for the cars the same, but move all the percentages in reduction to other modes that we want to shift the model split to. And the last one, we bring a great benefit for the city and for the life and for the environment. And we have to work on getting some appropriate appreciation for that. And I give my appreciation to your attention. Thank you very much.